Now, let us look into another problem as per which there is a one-sided function f of t given. It has a Laplace transform of f1 of t, sorry, f1 of s. There is a delayed version of f of t which is given as f of t minus tau, which has a Laplace transform of f2 of s. It's also given that f1 star of s is complex conjugate of f1 of s, where s is equal to sigma plus j omega. It's also given that g of s is equal to f2 of s multiplied by f1 star of s divided by mod of f1 of s whole square. We need to find the inverse Laplace transform of g of s. So please note that f of t minus tau is the delayed version of f of t, and the corresponding Laplace transform of f2 of s, which can be written as e power minus s tau f1 of s. So upon substitution, we get that g of s is equal to e power minus s tau f1 of s multiplied by f1 star of s divided by mod of f1 of s whole square. But we know that f1 of s multiplied by f1 star of s is equal to mod of f1 of s whole square. So the corresponding terms in numerator and denominator get cancelled to get g of s as e power minus s tau. From this we can write that L inverse of g of s is equal to delayed impulse, which is delta of t minus tau, that is the impulse at the instant tau. This is the required inverse Laplace transform. Now let us look into another problem as per which there is a step or there is a pulse which is given as shown in the figure. The pulse is present from t is equal to 3 to t is equal to 5, and it has a magnitude of 2. We need to find the Laplace transform of g of t. So from the given figure we can write that g of t is equal to 2 multiplied by u of t minus 3 minus u of t minus 5. From this we can obtain the Laplace transform of g of s. We know that Laplace transform of u of t is equal to 1 by s, and Laplace transform of u of t minus a is equal to e power minus as multiplied by 1 by s. From this, Laplace transform of g of t is equal to 2 multiplied by e power minus 3s into 1 by s minus e power minus 5s multiplied by 1 by s. So this is the Laplace transform of g of t. Now let us look into another problem as per which there is a signal x of t which is as shown. X of t is a ramp from t equal to 0 to 1 second, and it has a magnitude of 1, and its value is constant from t is equal to 1 to t is equal to 2. We need to find the Laplace transform of x of t. From the given x of t, we can say that x of t can be written as sum of three functions which are as shown in the figure. One is a unit ramp input which can be written as t into u of t. Other is a ramp with unit slope but starting from the instant t is equal to, sorry, other one is also a ramp which is starting from the instant t is equal to 1 but is of unity slope. And finally a unit step function which is of magnitude -1 as shown. So from this we can write x of t as x of t is equal to t into u of t minus t minus 1 multiplied by u of t minus 1 minus u of t minus 2. So from this we can write Laplace transform of x of t as 1 by s square minus e power minus s divided by s square minus e power minus 2s divided by s. This is because Laplace transform of t into u of t is 1 by s square and Laplace transform of t minus 1 into u of t minus 1 is e power minus s into 1 by s square and Laplace transform of u of t minus 2 is e power minus 2s into 1 by s. So whatever we obtained finally is the required Laplace transform. Now let us start looking into another problem as per which u of t is unit step function and r of t is ramp function. It's given that u of t star r of t is convolution between r of t and u of t. Now we need to find u of t plus 1 convolved with r of t minus 2. We know that Laplace transform of u of t is 1 by s. From this, Laplace transform of u of t plus 1 can be written as e power s multiplied by 1 by s. Similarly, Laplace transform of r of t is equal to 1 by s square. From this, we can write that Laplace transform of r of t minus 2 is equal to e power minus 2s into 1 by s square. From this, we can write that u of t plus 1 convolved with r of t minus 2 is equal to L inverse of Laplace transform of u of t multiplied by Laplace transform of r of t. So upon multiplying e power s into 1 by s with e power minus 2s into 1 by s square, we get L inverse of e power minus s into 1 by s cube. We know that L inverse of 1 by s cube is t square by 2 into u of t. From this, we can write that L inverse of e power minus s divided by s cube is equal to t minus 1 whole square by 2 multiplied by u of t minus 1. So from this we see that the convolution result of u of t plus 1 and r of t minus 2 is t minus 1 whole square by 2 multiplied by u of t minus 1. Now let us start looking into another problem as per which there is a signal f of t which is as shown in the figure. The function f of t is 1 in the range of 0 to 1 and it is 2 in the range of 1 to 2 seconds. We need to find the Laplace transform of f of t, where f of t is the given function. From the given f of t, we see that f of t can be written as f of t can be written in the closed loop form as u of t plus u of t minus 1 minus 2 into u of t minus 2. We know that for finding the Laplace transform of f of t, we know that Laplace transform of u of t is 1 by s, and Laplace transform of u of t minus s is e power minus s into 1 by s, and Laplace transform of u of t minus 2 is e power minus 2s into 1 by s. From this we can write that Laplace transform of f of t is equal to 1 by s multiplied by 1 plus e power minus s minus 2 into e power minus 2s. This is the Laplace transform of the function that we have shown. Now let us look into another problem, as per which it is given that there is a LTI system with impulse response h of t, and it is given an input of x of t. It's given that Laplace transform of x of t is equal to s plus 3 divided by s plus 1 into s plus 2. Also, Laplace transform of h of t is equal to s plus 2 divided by s plus 3 into s plus 5. If x of t is the input to a LTI system of impulse response h of t, we need to find the output y of t of the LTI system. So we know that y of t is equal to L inverse of y of s, that is equal to L inverse of x of s multiplied by h of s. So upon substituting for x of s and h of s, we get that y of t is equal to L inverse of 1 by s plus 1 multiplied by s plus 5. This can further be simplified by splitting into partial fractions as L inverse of 1 by 4 into s plus 1 minus 1 by 4 into s plus 5. So from this we can write that y of t is equal to 1 by 4 multiplied by e power minus t minus e power minus 5t u of t, because L inverse of 1 by s plus 1 is e power minus t u of t, and L inverse of 1 by s plus 5 is e power minus 5t u of t. From this we see that for a input of x of t, the LTI system of impulse response h of t gives the output of y of t is equal to 1 by 4 multiplied by e power minus t minus e power minus 5t u of t as per the given data. Now let us look into another problem, as per which there is a one-sided function f of t whose Laplace transform is given as 2s plus 3 divided by s into s cube plus 3. We need to find df by dt as t tends to infinity. We know that if 2s plus 3 divided by s into s cube plus 3 is the Laplace transform of a function f of t, Laplace transform of df by dt can be given as s into Laplace transform of f of t minus f of 0. So f of 0 is the initial value of the function, which can be written as limit t tends to 0 f of t, that is equal to limit s tends to infinity s into f of s. This is further equal to limit s tends to infinity 2s plus 3 divided by s cube plus 3, which upon simplification becomes 0. So from this we see that Laplace transform of df by dt is equal to s into 2s plus 3 divided by s into s cube plus 3 minus 0. This is upon substituting for f of t and f of 0. From this, we see that Laplace transform of df by dt is 2s plus 3 divided by s cube plus 3. Now, the value of df by dt as t tends to infinity can be written as limit t tends to infinity df by dt can be written as limit s tends to 0 s into Laplace transform of df by dt. This is from the final value theorem. Upon substituting for Laplace transform of df by dt, we see that limit s tends to df by dt as t tends to infinity gets simplified as limit s tends to 0 s into 2s plus 3 divided by s cube plus 3, which upon simplification becomes 0. From this we see that the value of df by dt as t tends to infinity for the given f of t is 0. Now let us look into another problem, as per which it's given that there is an LTI system which has simple poles at -2 and -4. It has a 0 at -3. It's also given that if h of s is the system function of the LTI system, h of 0 is equal to 1. From this, we need to find the impulse response h of t of the LTI system. So we can write that the system function transfer function of the LTI system can be written as, sorry, the transfer function of the LTI system can be written as h of s is equal to k into s plus 3 divided by s plus 2 into s plus 4. Please note that here the -3 is the 0 and -2 and -4 are the poles. From the given data, we know that h of 0 is equal to 1. So from this, we can say that k is equal to 8 by 3. So the transfer function of the LTI system becomes 8 into s plus 3 divided by 3 into s plus 2 into s plus 4. Upon splitting this one into partial fractions, we get that h of s is equal to a by s plus 2 plus b by s plus 4. So upon simplifying the summation, we get that 8 by 3 into s plus 3 is equal to a into s plus 4 plus b into s plus 2. Upon equating the terms corresponding to s and the constant term, we get that a plus b is equal to 8 by 3 and 4a plus 2b is equal to 8, which can further be simplified as 2a plus b is equal to 4. But we know that b is equal to 8 by 3 minus a. So upon substituting, we get that a plus 8 by 3 is equal to 4. That implies a is equal to 4 by 3. So from this, we can write that b is equal to 8 by 3 minus a. So b is also 4 by 3. So finally, we can write the transfer function of the LTI system as h of s is equal to 4 by 3 into s plus 2 plus 4 by 3 into s plus 4. So from this, the impulse response of the LTI system becomes h of t is equal to 4 by 3 multiplied by e power minus 2t minus e power minus 4t, sorry, plus e power minus 4t u of t. This is because inverse Laplace transform of 1 by s plus 2 is e power minus 2t u of t, and inverse Laplace transform of 1 by s plus 4 is e power minus 4t u of t. From this, we can write that h of t is equal to 4 by 3 multiplied by e power minus 2t plus e power minus 4t u of t. Now let us look into another problem, as per which It's given that there is an LTI system of impulse response h of t is equal to e power minus 2t u of t, and it's given an input of x of t is equal to e power minus 3 into t minus 1 multiplied by u of time minus 1. From this, we need to find the output y of t of the LTI system. For the given input of x of t is equal to e power minus 3 multiplied by t minus 1 multiplied by u of t minus 1, the Laplace transform can be written as Laplace transform of x of t equal to 1 by s plus 3 multiplied by e power minus s, and it's given that the impulse response is h of t is equal to e power minus 2t u of t. From this, Laplace transform of h of t is equal to 1 by s plus 2. From this, we can write that Laplace transform of y of t is equal to Laplace transform of x of t multiplied by Laplace transform of h of t, which upon simplification becomes e power minus s multiplied by 1 by s plus 3 into s plus 2, which can further be simplified as e power minus s multiplied as a whole multiplied by 1 by s plus 2 minus 1 by s plus 3. This is upon splitting 1 by s plus 3 into s plus 2 into partial fractions. We know that L inverse of 1 by s plus 2 minus 1 by s plus 3 is equal to e power minus 2t minus e power minus 3t u of t. So we also know that L inverse of e power minus as multiplied by f of s can be written as f of t minus a, where f of t is a one-sided function. So from this, y of t becomes e power minus 2 multiplied by t minus 1 minus e power minus 3 multiplied by t minus 1 as a whole multiplied by u of t minus 1. So for the given input, the given LTI system gives an output of y of t is equal to e power minus 2 multiplied by t minus 1 minus e power minus 3 multiplied by t minus 1 u of t minus 1. Now let us look into another problem as per which we need to find Laplace transform of cos of beta multiplied by t minus 2 multiplied by u of t minus 2. We know that Laplace transform of cos beta t u of t is equal to s by s square plus beta square. From this, we can write that Laplace transform of cos of beta into t minus 2 multiplied by u of t minus 2 is equal to e power minus 2s into s divided by s square plus beta square. This is because Laplace transform of f of t minus a, where f of t is a one-sided function, is e power minus as into f of s, where f of s is Laplace transform of f of t. Now, so from this we see that the answer of the given problem is e power minus 2s into s divided by s square plus e power minus 2 into s divided by s square plus beta square. Now let us look into another problem as per which it's given that Laplace transform of a one-sided function f of t is given as 1 by s square into s square plus 1. From this we need to find f of t. We know that Laplace transform of integral 0 to t g of u du is equal to 1 by s into g of s. So we use this identity to find f of t. We know that g of s is sorry, let g of s is equal to 1 by s square plus 1. From this we can write that g of t is equal to sine of t ut. From this we can write that 1 by s into L inverse of 1 by s into s square plus 1 is equal to integral 0 to t sine of u du. This is using the identity that we have shown before. From this can be written as minus cos u with limits being t to 0. This upon simplification becomes 1 minus cos u, 1 minus cos t dt. So 1 minus cos t u of t. Similarly, we can show that L inverse of 1 by s square into s square plus 1 is equal to integral 0 to t 1 minus cos u du. This is using the given identity itself. This can further be simplified as u minus sin u with limits being t to 0. This upon simplification becomes t minus sin t u of t. From this we see that if L of f of t is equal to 1 by s square into s square plus 1, f of t can be written as t minus sin 2 t minus sin t multiplied by u of t. This is the required answer. Now let us look into another problem as per which there is a LTI system of impulse response h of t is equal to delta of t minus delta of t minus 1. It's given an input of x of t, which is as shown in the figure. The input x of t is a pulse from t is equal to 2 to 3 seconds and it has a magnitude of 1. We need to find the Laplace transform of the output of the LTI system for the given input. If h of t is equal to delta of t minus delta of t minus 1, Laplace transform of the impulse response, that is h of t, can be given as 1 minus e power minus s. Also, the input in the unit step function form can be written as x of t is equal to u of t minus 2 minus u of t minus 3. From this, we can write that Laplace transform of x of t is equal to e power minus 2s minus e power minus 3s divided by s. From this, we can write that Laplace transform of y of t is equal to Laplace transform of x of t multiplied by Laplace transform of h of t, which is equal to e power minus 2s multiplied by 1 minus e power minus s whole square divided by s. This is upon multiplying Laplace transform of x of t and Laplace transform of h of t. So the Laplace transform of the output is e power minus 2s multiplied by 1 minus e power minus s whole square divided by s. Now let us start looking into another problem as per which we need to find the Laplace transform of sin h 2t multiplied by sin 3t u of t. We know that sin h 2t can be written as e power 2t minus e power minus 2t divided by 2. From this, the required Laplace transform can be written as Laplace transform of 1 by 2 multiplied by e power 2t minus e power minus 2t multiplied by sine of 3t ut, which can further be simplified as half multiplied by Laplace transform of e power 2t sine 3t u of t minus Laplace transform of e power minus 2t sine 3t u of t. We know that Laplace transform of e power alpha t cos omega t, sorry, sine omega t ut can be written as s, sorry, omega divided by s minus alpha whole square plus omega square. From this, the required Laplace transform can be written as half multiplied by 3 divided by s minus 2 whole square plus 3 square minus 3 divided by s plus 2 whole square plus 3 square, which upon simplification finally becomes 12s divided by s power 4 plus 10s square plus 169. So the Laplace transform of sin h2t sin 3t ut can be obtained as 12s divided by s power 4 plus 10s square plus 169. Now let us look into another problem as per which we need to find Laplace transform of t into sin of a t u of t. We know that the Laplace transform of sin of a t u of t is equal to a divided by a square plus a square. So from this we can write that Laplace transform of t into sin of a t u of t can be written as minus d by ds of f of s, where f of s is the Laplace transform of sin a t ut. So this is equal to minus d by ds of a by a square plus a square. This upon simplification becomes 2as divided by a square plus a square whole square. So from this we see that the Laplace transform of t into sin a t u of t is equal to 2as divided by a square plus a square whole square.